So when I was preparing my talk for now, I realized that it's neither going to be very specific about volcanism or the La Palma eruption, but I just kind of happened to be in both in the to tie in my research. So I actually study the behavior of the Earth's magnetic field, and that's well, that's where it already starts being a bit odd if you come into a talk about volcanism or the La Palma eruption. But as it turns out, it's actually going to be important. The Earth's magnetic field protects us against electromagnetically charged particles from the sun. So the Earth is constantly bombarded by these particles, and they are deflected by the Earth's magnetic field. That's the main well, that's what the Earth's magnetic field is kind of famous for, at least. But what is less known is that the Earth's magnetic field is also highly dynamic. So there's currently kind of a hole in the Earth's magnetic field. It's called the South Atlantic anomaly. The field is stronger towards the North Pole, towards the North and the South Poles, and there's this kind of deviation. It's about half as strong as you would expect over the area of South America, and that thing causes issues. And so, for example, this image is again, the field lines are the gradient of the magnetic field. So the red colors are the higher magnetic fields, and South Atlantic anomaly again is underneath South America. And the yellow dot is the location where we get an upset in the system of one particular satellite. So every time there is an upset in the system, and you should really think of that as a kind of just a bit flip in the electronics of this satellite. And every location where that happens is indicated by a yellow dot. So these yellow dots, they cluster underneath this hole in the Earth's magnetic field, and that is because their excess magnetically charged particles from the sun are closer to the Earth's magnetic field, and that's where they interfere with the electronics on board the satellite. So this is one of the examples that we used, that I used to get my funding, at least. Then we have to. Oh, I don't know. My computer is kind of going through my slides by itself, which is a bit awkward. So then you have to make the step from the so if you want to know how this Earth magnetic field behaves through time, we have to kind of reconstruct it. So we need a kind of recorder of the Earth's magnetic field that is available all over the world and for all time spans, basically. So I'm particularly interested in these effects like the South Atlantic anomalies. These kind of phenomena, relatively short-lived, so they move on decadal to centennial timescales. But luckily we have these recorders available, especially on these timescales, in the form of volcanic material. So in basalt, so in extrusive volcanic material, there's a lot of iron. And these iron oxides, they become magnetic, slightly magnetic, during when they cool, basically, and in the Earth's magnetic field. So they capture the Earth's magnetic field for that particular location and that particular moment in time when they cool. So, for example, here's a map of the southern tip of. Nope, I'm not. No, my computer is kind of flipping through things, but here is the map of the southern tip of Hawaii, and each individual lava flow is indicated by a specific color, and this I was talking about this one still, and each individual is indicated by a color. So that is kind of the by sampling all these individual lava flows that have their own specific age, you can make reconstructions of the Earth's magnetic field behavior for this location through time. So we did this for Hawaii, and we did this for, this is the southern tip of La Palma. That's where it starts becoming more familiar, I guess. So La Palma has had regular eruptions through time. So there is the 1949, the 1971 flows. But also older flows that are 1712, 1585. So they are visible on the island, especially the 1971 flow was especially present, obviously. And now there is this whole big new 2021 flow that's actually to the north of this, the northernmost 49 flow. So we have these perfect recorders. So you would say, well, this is the best job you can have. You fly out to all these volcanoes, you sample these lava flows, and you reconstruct the Earth's magnetic field through time. That's great. So that's what we like to do. So we take our samples from these volcanoes. But the main issue is that these experiments, especially to assess the intensity of the Earth's magnetic field, are very time consuming, and these are typical success rates. So we take out, if I take out my PhD candidate, or what I did myself during my PhD, we spent like 2 weeks on this volcano. You take along tens of kilos of material, and you work on that for at least half a year in laboratory because these experiments are so time consuming. And then you end up with success rates that are in the order of 10 to 15%. So you have to check out almost 80% or more of your data, because these techniques that we use, they have kind of a flaw that I will get to in a minute. Even more so, if these 20% of the data that are accepted would actually be reliable, then it would still be worth the effort. But this is a comparative study of at least 12 studies that were done on one specific lava flow from the 1960s from Hawaii. And these are results that were deemed successful by these individual studies. So they get data points between like a little over 20 and up to 70 microtesla. But that spread in data points that were deemed accurate for this particular lava flow, that is the same variation, that is the total variation between the equator and the South Atlantic anomaly and the North Pole. So basically the only thing you can show on this flow based on this data is that the Earth has a magnetic field. But that is something we were already pretty sure about, and we want to know these variations in time and space. So these are the problems with these paleointensity techniques, at least. So that doesn't sound as the best advert for a PhD position, but still people wanted to come. That's great. So what I did, I was pretty annoyed by this during my PhD. I spent 4 years on this, and I worked on this, and I had to check out 80% of my data, and the other 20% was iffy at best. I was thinking, and I said, well, is there something we can do to overcome this? So what I did is I went to the microscopy people, and they said, well, we have these we have all these iron oxides in our in our samples. So what you're looking at now is a microscope photo, just optical microscope photo, and these iron oxides are typically under these lights, so are these bright yellow dots. So all these bright white grains, they have their own magnetic moment when they cool, and what we measure is just the magnetic moment of the entire sample, the bulk sample. But all these grains, some grains might have a reliable magnetic moment, while other grains present may be a less accurate recorder of the Earth's magnetic field. So when there are a lot of these less accurate magnetic recorders, and less accurate, like larger grains, are known to be have more complex behavior magnetically. Chemically complex grains are more difficult. So what we're looking at, what we would like to have, is these very tiny pure magnetite grains in our sample. But well, we cannot. These larger grains are also present. So we measure, when we measure a bulk sample, we measure all these grains at the same time. So what I was then thinking is, can't we just calculate or determine the magnetic moments of individual grains in our sample, so that we can just weed out these bad grains in our sample? That's when I started all kinds of collaborations with groups in nanotechnology, even material sciences, and also in groups working in this imaging. So what we now know as micromagnetic tomography technique is that we combine a surface scan. So we don't measure the bulk sample anymore in total. So we don't. Otherwise, we put the bulk sample in a machine. We get one number. We get one magnetic vector out of that. But now we make a magnetic scan of the magnetization on the surface of a sample. And we combine that with micro-CT information. So with this micro-CT information, we determine, of course, it's interpreted as density variations usually. And these iron oxides, they have densities that are well into 5,000 kilograms per cube. So it's in the micro-CT, it's relatively easy to select these iron oxide grains in a sample. So if we now combine these two data sets, we can calculate what the magnetic moment of these individual iron oxide grains in a sample would have been through a mathematical inversion. This is actually a technique that we borrowed from seismology. So from image information from outside the body, we try to infer information on these particular grains inside it. So this is a mathematical inversion that we did. And so we tested this. So on the left-hand side, you see an optical image of the of a particular little bit of lava, so a little tiny basically section of a thin section. You see the optical image with these other larger minerals in the backhand, and the blue and red colors are the magnetic scans. So these are zones with higher and lower magnetizations on the surface. So if you now zoom in onto this area 2 here in panel B, you see what we have in white. We have the outlines of the iron oxide grains as they are determined by the micro-CT image. So we know that the magnetization in this area can only arise from these white outlined grains that are present in the samples, because the other minerals are just do not have magnetic properties. So then we have in panel C, we have a map of the magnetization that we can actually, that's actually the residual. So the lower the magnetizations in panel C, the better the magnetization of the grains are resolved. And again, you see that these smaller grains have lower residuals, so we can better determine their magnetization than these very larger complex grains that are also in the panel. And that leads us to that we can, for example, assess the magnetization or the magnetization, the big capital M, or the magnetic moment, smaller m, of grains as functions of their diameter. So we now have a technique that we can use to determine the magnetizations of all these grains individually, and also to start weeding out grains with poor recording properties. So for example, you could disregard the magnetic signal of these larger grains that are present and just consider the magnetic contributions of these smaller grains that are better resolved by our new technique. And in that, that would greatly help us to improve both the success rate and the accuracy of our experiments. So what you need for that is a big micro-CT scan. So for this one, we used the one at TU Delft. We need very low resolution because we need to detect the smaller grains. We are now pushing the limits even further, really towards the nanometers or tens of nanometers range. That's what we're looking for. And we combine that with a magnetic image, a magnetic scan. So you can easily use a magnetic scanning squid setup. Squid is a superconducting quantum interference device. It's kind of a difficult technique to measure magnetizations, but it's highly accurate. Only drawback is that it needs to work at 4K, so you need to submerge your sample into this 4 Kelvin, so into liquid helium basically. So that messes with the magnetization. Then there is this magnetic tunnel junction scanner technique that we used at the University of Cambridge. There's a different scanning technique. There's a very tiny pickup loop where you actually measure the magnetization. It's kind of looks almost to a similar setup as an AFM setup or MFM setup. And then there is the new kid on the block to measure magnetization on surface. It's a quantum diamond microscope developed at Harvard University. And it measures magnetizations because magnetizations cause interfere or cause a difference in fluorescence effect in nitrogen vacancies in a little diamond chip. So what you're measuring magnetizations here as function, basically, but it's just with an optical camera. So you measure the magnetizations through the effect, the fluorescence effect that they cause in this quantum diamond microscope. So that's the one that we're also building in Utrecht here in the laboratory. So we are almost done. Or actually, it makes images now. So it's a technique where the laser comes in from the right. You have the sample underneath, and the optical tower is above the sample. It's almost near in construction. But then this is a seminar on volcanology and on La Palma. So why did La Palma, so where does this La Palma become important? So this is a very new technique that we're developing, also my ERC starting grant. And so what we need is sample material for which we actually know the answer. So what we did, as soon as the La Palma eruption took place, we made plans to sample the very newest volcanic material that we could find and measure the magnetic field that it actually cooled in. So then we have volcanic material for which we know the answer. So here we are on this on the 2021 eruption of on La Palma. So this is Romy, who's a PhD candidate. So we worked so we actually measured here on the left-hand side, left-hand image. The outer end of that thing has a fluxgate magnetometer. So we actually measure the magnetic field that this lava cooled in. And then subsequently we took our samples as we routinely do that in our paleomagnetic study. So here we actually gathered a sample set for which we actually precisely know the answer or the outcome of what the outcome of our experiments would be. And we have the samples as we would normally take them in the field. So this is about the best calibration set for our MMT studies that micromagnetic tomography studies that we can wish for. So in the time that we were on the island in late October, we managed to sample 3 sites. We were only there for a short, limited amount of time because these samples needed to be back in the laboratory to avoid viscous or magnetic contamination. So we took them out to the laboratory pretty quickly. In between it, we were there, and the end of the eruption, in that last 2 weeks, the volcano managed to destroy all our 3 sites, so we cannot go back. That's a bit of a bummer. So there was slightly more lava here to the north and to the southwest. In between, we were there and the end of the eruption. So we are now processing this data from the traditional paleointensity experiments. We see that they are actually pretty well behaved. So we have probably a lot of these tiny grains in our material. So this is about the best calibration set that we have for the development of our new micromagnetic tomography technique that we could wish for. So now kind of it all ties together, volcanoes tie together, Earth's magnetic field ties together, also the techniques in the multi-scale laboratory project are tie into this, and this 2021 eruption on La Palma. So to summarize that, we started off with that lava is our only source of information on the past behavior of the Earth's magnetic field that are widely available. The traditional paleointensity techniques that I worked on during my PhD have low success rates and are iffy at best. And this new micromagnetic tomography technique holds some potential to provide more accurate paleomagnetic data, even with very challenging recorders. And this 2021 eruption is actually the best natural laboratory that we could wish for for our experiments.